Here is the gamma density. Since it is a product of a power of x and an exponential of x, we have seen how multiplying with any further power of x still leaves it in this form. As a result, the integral may be evaluated in terms of the gamma function. The same thing holds even if you multiply it with some further exponentials. We are going to use this property in order to find its characteristic function, which is defined as e to the power itx, expectation of that. So I take e to the power itx, multiply it with the density and integrate. X to the power alpha minus 1 remains as it is. Now for the exponential thing, I want to write it as minus something x dx. I already have p and I have it. Because I have a minus, I will put minus it. Now I shall use that trick which I mentioned earlier also, that I will treat this just as a constant and will not be bothered by the fact that it is actually a complex constant, because anyway I can split it up into cos and sine and justify whatever I am going to do right now. So this is as if it is just a constant, so it is again of the gamma integral form. So this will be p to the power alpha by gamma alpha, just the constant. Now the role of alpha is still played by alpha, so upstairs I will have gamma alpha, no problem. The role of this rate is, instead of p, it is now played by p minus alpha minus it, so p minus it whole to the power alpha. These two things nicely cancel each other off, leaving us with p divided by p minus it whole to the power alpha. And remember, when we work with characteristic function, t may be any real number. Once you get this characteristic function, certain results are rather obvious and they are very useful. Suppose I have some random variables that are independent, x1 to xk, and they have a very similar distribution. They are not identically distributed, but all of them are gamma, same p, but the alpha parameter, the shape parameter, may depend on I. In that case, it is very easy to compute the distribution of the sum. That must have distribution which is again gamma, again the same rate parameter, and here we will just have summation alpha I. And why is this true? Super trivial, because the characteristic function of this, we already know from property of characteristic function, is product of characteristic function of the individual xi's, because they are independent. And I hope you have not forgotten why this holds. This holds because by property of exponential, this thing can be split like this. Incidentally, I am using I both as the index as well as the complex size. Hopefully you are not too confused with that. Now since xi's are all independent, so expectation will split over the expectation. Each of them has finite expectation. They are bounded quantities. And now we shall just use this fact. Observe that this thing remains the same for all the xi's, because p was the same for all the xi's. So all these exponents add up together, and we find that this indeed is the characteristic function of the gamma distribution. But now we also know that characteristic function characterizes a distribution. So since this random variable summation xi has the characteristic function of the gamma distribution, so it must have this distribution. Since it is the characteristic function of gamma, so summation xi must have that distribution. This line is very important since characteristic function uniquely determines the distribution. Now we can use this result to show a relationship between the gamma distribution and the exponential distribution. This is our familiar gamma density. Let us see what happens if I put alpha, the shape parameter, equal to 1. This will remain unaltered, e to the power minus x. This will just not be there. This will simply become p, Downstairs you will have gamma 1, which anyway we know is 0 factorial, that is 1. So it is this when x is positive and 0 else. We quickly recognize this as our familiar density for exponential with rate p. So exponential family or exponential distribution is a special case of the gamma distribution. We saw how we can go from gamma to the exponential thing by setting the shape equal to 1. Now we can do the other way around also. If x1 to xk are IID exponential p, identical distribution, so same p, then summation of xs will have a gamma distribution. Can you guess what it is? Not very difficult. Just remember that this exponential p is the same as gamma p1. So all of them are independent with gamma same p and all of them 1. So it will be, by our earlier theorem, 1 plus 1 plus 1, all these shapes add up, and how many are there? K many. So this will just be, of course I must write p, then k. So that is an interesting result. Sum of IID exponential has the gamma distribution. With this theorem still on screen, try to do this. I give you the CDF of gamma p alpha as a notation. In general, it is quite difficult to compute it. One has to use numerical methods to compute it. But suppose I give you this function. Now, x1 to xk are IID, very much like this setup. I give you a value for p2. Your job is to express probability that x bar is less than or equal to 5. When I say x bar, well, I will make it concrete, so I will make it 10. So x bar means average of these 10 random variables. What is the chance that this is less than or equal to 5, and express it in terms of this capital F function. So typically in a computed system like R, you will have a function to compute this for you. When you want quantities like this, you have to manipulate, do some little algebra, use this result, etc. to reduce it to that function.